Hello. So today in this video, we'll try to together solve one UMP, which is the utility maximization problem together. And in this example that we're using is this called Cobb-Douglas utility function. Okay. So and we will also try to use the Kuhn-Tucker conditions, which is a more general way to solve the optimization problems. Okay. So the reason that Kuhn-Tucker conditions are more general, this is simply because that sometimes if we simply use the first order conditions to solve those optimization problems, then we might miss the corner solutions. That it means that if those axes are they're zero. Okay. So, but if we're using the Kuhn-Tucker conditions, then we can extensively or fully discuss all those possibilities, okay, for all those values, because we will list and exhaust all the possible cases. Okay, good. So now let's begin with this example. All right. So here we have this Cobb-Douglas utility function. Okay, so this consumer is choosing the levels of x1, x2, and here x1 has a power of alpha and times x2 to the power of 1 minus alpha. Okay, so and by choosing x1 and x2 to try to maximize this utility function. So the constraints are such that, so first this person has a budget, right? So the sum of those p1x1 plus p2x2, it has to be no larger than w, the wealth. Okay, so and second and third constraints are such that those consumption bundles, we have to have non-negative values for each of those. Okay, so x1, x2, they have to be greater than or equal to 0. So those x1, x2, those are the choice variables for this consumer, and all the other notations are just the scalar numbers, just the numbers, right? But maybe not scalars, but they are constant. Okay, so here this we say that we have some assumptions where this alpha is a real number between 0 and 1, not including the boundaries, and p1, p2, and w, they're all positive. Okay, good. So right, so those are all scalars, right? Because we write x1 and x2 separately. So all the prices and w's, they're scalars. Okay, so before we solve this problem, so some point important to notice is that because if some preference relation, okay, that can be represented by some utility function, okay, such as this Cobb-Douglas, then for any strictly increasing function, and then let's say this f, which is a strictly increasing function, then we can say that this, so this is mentioned before, right? So then we can say that this preference relation, it can also be represented by the compound function of f and u, okay? So we can simply transform this utility function, use some other strictly increasing function to make this calculation easier, okay? So we simply choose the log to take the transformation for this Cobb-Douglas utility function, okay, to take the power, to put that in front of those axes, okay, and then make the product as the addition. Okay, good. So after the transformation, then this t function becomes this. Okay, so it's alpha log x1 plus 1 minus alpha log x2, and the constraints remain the same. Okay, so now we'll start to try to solve these problems using the KKT or KT conditions. Okay, so and again, so the reason why we're using this more general approach is to try to avoid the problem of missing some corner solutions that we might miss if we just use the first order conditions instead. Okay, so how do we use the Kuhn-Tucker conditions? So first, we need to set up the Lagrangian. Okay, so this calligraphic L, which is a function from the all those parameters x1, x2, and we also treat those coefficients or those multipliers that we put in front of those constraints to be also some variables for this function in this Lagrangian only. Okay, and that'll be function mapped to this to a real number. Okay, so in full, this Lagrangian, this calligraphic L, it equals alpha times log x1 plus or minus alpha log x2, and then plus something else. So here we put some multipliers such as lambda for the first constraint here, and mu1 for the second, and mu2 for the third. Okay, so and we put all those, and then we need to arrange those inequalities to be with the correct sign or the correct direction, such that this w minus p1 x1 minus p2 x2, this has to be greater than or equal to 0. So in this direction, okay, so that we can put this positive sign here. And then we do the same thing for the second constraint and for the third constraint, and then we add those up together to set up this Lagrangian. Good. So that'll be the first step. Okay, and then we need to list all the necessary conditions. Okay, so those conditions include a wide range or a lot of conditions. Okay, so the first set of conditions would be called stationarity. Okay, so do not just so those are just pretty straightforward, right? Don't think it too complicated, but those stationary conditions are just the first order conditions. Okay, so we simply take the derivatives, okay, of this Lagrangian with respect to x1. Okay, so this becomes the first equation here, and then we take the first order condition. We take the derivative, the partial derivative with respect to x2 from the Lagrangian, and this becomes the second. Okay, good. So this is the stationarity conditions, and then we have the feasibility constraints. So we have two kinds of feasibility. So the first kind of feasibility constraint is called primal. So the primal feasibility is simply just the original constraints that we have in this problem. Okay, so those would be just those subject to constraints. Okay, so here we have those copy and paste to put it here. Okay, and the other kind of feasibility constraint is called dual feasibility. Okay, so those are just the feasibility constraints that we put for all those parameters or for those multipliers. Okay, so we simply say that all those multipliers, they are greater than or equal to 0. Okay, so the last set of constraints that we put here is called complementary slackness. Okay, so if you want to have a further look on the theories of Kuhn-Tucker conditions, or why do we need those conditions, you might have a look and search for some information on that. But here we won't get to explain too much about that, but simply the intuition of having those complementary slackness is such that if we multiply those multipliers and with the part in those constraints, in those primal feasibility constraints, so simply the complementary slackness are just the combination of those two kinds of feasibility constraints. Okay, and if we multiply those different parts together and set this to be 0, and this would be helpful for us to further simplify the calculations when we're solving some optimization problem. Okay, and you'll see this intuition as we solve this later. Okay, so we do this the same as for the second constraint, for the second primal feasibility constraint, where we have this mu1 x1 to be 0, and then the same for the third, mu2 x2 to be 0. Okay, good. So in brief, the underlying intuition of this complementary slackness is such that if we have this lambda to be 0, okay, so we can either have this lambda or this constraint, this part to be 0. Okay, so or they could be the 0 but at the same time, but it cannot happen here. Okay, so we simply have those possibilities, and those will be useful for us to later to solve those system of equations and inequalities. Okay, good. So those are a lot of constraints that we have in this problem, and then we are ready to solve this. Okay, so let's begin from 1 and 2. Okay, so from 1 and 2, we can immediately observe that if we have zeros for x1 and x2, then those equalities in 1 and 2, they cannot hold. Okay, simply because that we have those constraints for those numbers. Okay, so if we have x and x2 to be 0, then the first terms will be infinity. Okay, and then this equality they cannot hold anymore. So in other words, x1 and x2, they cannot be 0. Okay, so that's why we write those here. And then we use 4 and 5. So 4 and 5 together, they tell us that x1 and x2, they can be greater than or equal to 0. Okay, and here we said that x1 and x2, they're not 0. So it means that here what we can infer is that x1 and x2, they cannot be 0, and at the same time they have to be strictly greater than 0. Okay, good. Now we combine 10 and 11. Okay, so now we know that x1 and x2, they're strictly greater than 0. Okay, so remember that what I have said is that now because we have mu1 x1 to be 0 and mu2 x2 times they time together to be 0. So because of x1 and x2, they're strictly greater than 0. So we have mu1 and mu2, they have to be 0 both at the same time, right? To make 10 and 11 hold. Okay, so and after we have mu1 mu2 to be 0, and then we use 1 and 2 again. Okay, so we simply plug mu1 and mu2 to be 0 into 1 and 2. Okay, so and then we're able to solve to simplify 1 and 2. Okay, so what we have from 1 and 2 is alpha over x1 times p1 equals lambda. Also 1 minus alpha over x2 p2 equals lambda as well. Okay, so from those two, we can connect those two or plug in lambda to each other. Okay, and then we have a relationship between x1 and x2. Okay, and also from this, we can also know that this lambda cannot be 0. Okay, because of the properties of those terms. So now we know that lambdas cannot be 0, and we use 6. So 6 says that lambda has to be greater than or equal to 0. So now we know that lambda is not 0, so lambda has to be strictly greater than 0. Okay, then we use 9. So in 9, we said that now we know that lambda has to be strictly greater than 0. So this part, it has to be 0 to make this equality to be 0. Okay, so we have this part to be 0, and then we use the relationship between x1 and x2 and this constraint here to be binding, and we use those two, which is just a system of two equations with two unknowns, and then we can solve x1 and x2 respectively. So x1 will be alpha w over p1, and x2 will be 1 minus alpha w over p2. So that will be the only solution that we have in this problem. And with this set x, p, and w, we only have one value for that. Okay, with this only one single value because of the property, the convexity, right, for this uniqueness. Okay, good. So this will be a full example of how to use Kuhn-Tucker conditions or KKT conditions to generally solve this optimization problems, right? So and we can see from here is that, so finally what we have, so necessarily what we are using here is the relationship between x1 and x2. So this could be obtained from the first order conditions. Okay, and this one will be simply from the binding version of the budget constraint, right? So the other two constraints that x1 and x2 are greater than or equal to 0, so those are not binding. Okay, so we simply have the x1 x2 to be strictly greater than 0 in this case. Okay, so it means that in this case we do not have corner solutions, and therefore those, if we just use the first order conditions and the budget constraint to solve this problem, and we will get the same answer as we just did in the Kuhn-Tucker conditions. Okay, so for example, let's see. Okay, so let's say if for example, in some pictures, let's draw some figures to illustrate the idea of this. So this would be x1, okay, x2. So what we have solved would be something like this. Okay, so this would be the budget, okay, and this would be an indifference curve, which only has one tangent point to this budget set. Okay, and where this would be the x, or we can call this x star. Okay, in this set would be the only one single value for this solution set. Okay, so that would be in this case, okay, with Cobb-Douglas utility function. But so however, if sometimes we might not get this, this is called interior solution. Okay, sometimes we might get corner solutions or boundary solutions. Okay, so in this case, we have to use the Kuhn-Tucker conditions, or the Kuhn-Tucker necessary conditions. Okay. Okay, so for example, I have x2 here, x1. It's not straight. Okay, x1. Okay, let's suppose now we have this budget. As before. Okay, now this utility function, it doesn't look like the one on the left. It doesn't look like before. Okay, now it's such that, so it looks like this. Okay, and now if we move this utility function to the right, or move this higher or to the right, then we can see that the only tangent point or only solution would be in this corner. Okay, so at this point, this is the intersection of this utility function and this budget constraint. Okay, so in this case, we can see that the value of x2 would be 0, right? So as we did in this for those constraints, right? So x2 will be 0. So in this inequality here, so we have to let x2 to be 0, and this mu will be would not be 0 anymore, right? Okay, so those would be different cases, right? Including interior solution and boundary solution that we might face for different kinds of utility maximization problems, right? So Kuhn-Tucker conditions will be a much more general way for us to solve those optimization problems. Okay,